All right, so with this lecture, we're going to discuss complex numbers. This is a very important aspect of mathematical physics. It's an important aspect of physics itself. A lot of useful mathematical techniques stem from complex numbers. It allows us to solve particular equations that were thought impossible to solve in the past. It allows us to manipulate equations, manipulate solutions, and then take away from those solutions the realistic, actual answers we're looking for. Because, of course, if we're going to do physics and we're going to measure things, we're doing observables, let's say quantum mechanics, and we want to know what is the probability of finding a particle in a particular location. Well, obviously, that probability has to be a real number. It's 20% or 50% or whatever it is. There's no such thing as a complex number percent of finding something in the real world. Of course, if you're doing pure math and you live in a more abstract theoretical regime, then there's nothing wrong with that kind of thing per se. But in physics, we're dealing with real-world applications, and thus any physical, observable, any measurable thing must be a real number. However, sometimes it's either difficult to solve those equations that will give us the real answers, or impossible to do it without using complex numbers. So we're going to investigate how to use complex numbers. We're going to start from the beginning if you've never seen it before, and then go from there, complexifying and getting more and more interesting as we go. So first of all, a complex number. The big thing we need to know, everything stems from a particular equation, and that equation is x squared plus 1 is equal to 0. Now, normally this wouldn't be a big deal. All you have to do is, of course, algebraically solve this. We get x squared is equal to minus 1. To solve this, of course, we take the square root of both sides, and we would find that x would have to be equal to plus or minus the square root of negative 1. And for the longest time, this was like, oh, obviously this doesn't make sense. I mean, what number can you multiply by itself to give you the answer of negative 1? There is no number. If you try negative 1, of course, negative 1 times negative 1 just gives you positive 1. If you try 1, 1 times 1 is 1. There's no way to multiply a number by itself to get an answer negative 1. And so even mathematicians said, well, obviously that means that the original equation, x squared plus 1 is equal to 0, just does not have a solution. And if that's the case, then there's infinitely number of equations that don't have solutions. And that's a bad thing. We don't want a whole range of equations to just not be able to be solved. So mathematicians said, okay, what we're going to do, we know there's no real number which would solve this equation. So we're going to invent a new class of numbers which will be the solutions to these equations. Now, whether that is useful in the real world, whether that is meaningful physically, we don't care about it. All we care about is we've now developed something that allows us to solve these equations which were originally understood to be impossible to solve. And so what they did, they said the answer to this equation is the letter I, or the complex number I. I, of course, stands for imaginary number, just to differentiate it from real numbers. And so they said the answer to this equation, of course, we could have plus or minus I. I being now defined as the square root of negative 1. Okay. And of course, there's more. Of course, you could have the equation x squared plus 2 is equal to 0. That would mean x squared is equal to minus 2. So x is equal to plus or minus the square root of minus 2. And I say, well, wait a second. what's the answer to this? Because I is the square root of negative 1. This is the square root of negative 2. It's a completely different answer. And well, what they developed was we could do algebra with this complex number, I, pretend like it's just a regular number, and we just manipulate it. We could add things to it. We can multiply things to it and develop and build up more and more solutions to more and more of these equations. And so that leads us to the general form of the imaginary number, or complex numbers. And that general form says a complex number z, that's the kind of the variable, the general variable for a complex number, is a number of the form a plus I times b, where a and b are real numbers. So your standard 1, 5, negative 2.37, pi, those are all real numbers. So an example, we can have a complex number being 5 plus 2i, right? And this would be the same as saying 5 plus 2 times the square root of I. And then you can make any sorts of things. You could have z is equal to minus 3i. Well, that just means a is equal to 0 and b is equal to minus 3, right? So any complex number z can be written in the form some number plus I times some other number. Now, these are given names, a's and b's. Turns out a we call the real part of the imaginary number z, and b is called the imaginary part. Which makes sense, right? A has no I on it, so it's just the real number a. And b is a real number, but is being multiplied by this imaginary number I, so we call b the imaginary part of the complex number z. Now notice, this is not I times b, okay? Just b. So, for instance, in our example up here of 5 plus 2i, the real part, sometimes just re, is equal to 5, and the imaginary part, im, is 2, not 2i. That's very important. The I doesn't come with it. The imaginary part is just the number 2, even though, obviously, in the complex number is 2 times I. Okay, so if you have some complex number z, and someone says, what's the real part of the number? It's the part of the number that doesn't have the I on it. And if you're asked, what's the imaginary part of this number? You take the coefficient that's multiplying the I. Very, very easy. All right, now, once we have this, we say, well, let's say we have two complex numbers, z1 and z2. If z1 is a plus ib, and z2, let's say, is c plus id. Okay, so two random complex numbers. What can we do with these things? Well, can we add them together? And if so, how do we add them together? And this is one of the things you have to be very careful of when you do mathematics. It does not always follow that just because we've gained more mathematical knowledge and we have more mathematical tools, that those tools will follow the same rules as previous tools do. We're all used to, in basic algebra, things like commutative, or the commutative property, the associative property, distributive, all sorts of things like this. Well, it may hold that complex numbers also follow the commutative property or the associative property, but it may not. And you've seen examples of this in the past doing physics when we talk about vectors. When we do vectors, we've seen that adding numbers together, scalars, you just add them like you know how to add numbers. But when you add vectors, all of a sudden we have to be very careful. We can't just add two vectors together because they may point in different directions, and then the question becomes, how do you add directions together? And so we have this mathematical manipulation we do of getting x and y components, and then we add the x components together, and we add the y components together, and then we do magnitude and direction after that, all sorts of stuff like that. And in fact, as you progress further with vectors and vector calculus and all sorts of stuff, you find that it may be that doing a multiplication one way is the inverse of doing it the other way. Or when you do matrices, if you have a matrix or a vector, a matrix and vector together, let's say you want to multiply them together, well, if you multiply the vector A times the matrix M like this, it does not mean the same thing as the matrix M times the vector A like that. You don't get the same answer. They mean completely different things. Now, we're not going to get into matrices yet, but that is part of the course. We will get to matrices and linear algebra and things like that. But suffice to say, when confronted by a new mathematical tool or technique, before you just willy-nilly go doing all your previously known mathematical things with it, we have to be sure that mathematicians, because I'm assuming we're not mathematicians, we're just physicists right now, you have to be sure that the mathematicians have gone through and made sure that the rules of how to work with these things hold the way you think they do. Now, it turns out that the way you add complex numbers together is very, very similar to how we add vectors together. Okay? If we're going to add these two complex numbers together, z1 plus z2, to get an answer, the question becomes, well, some of the numbers have i's on it, some of the numbers don't. How do I work with this? And what you're going to find as we continue talking about complex numbers, in fact, the next lecture we'll get a little bit more into it, is you could think of a complex number as a vector. And just as a vector, let's say a two-dimensional vector has x and y components, so it's an arrow that sticks out in a certain direction. Complex numbers likewise can be thought of as a vector, but instead of x and y components, we have real and imaginary parts. And so just like when you add two vectors together, a and b, you add the x components together to get a number, and then you add the y components together separately to get a different number. That's what we're going to do here. When you add two complex numbers together, you add the real parts together. So z3, let's say, is the answer to this. And it's going to be the real part is a plus c added together. That's the real part of 1 plus the real part of 2. And then you add the imaginary parts together, b plus d. And then you stick the I on there. Okay. Another way of thinking about it is, let's say we have an equation. We have 5 plus 2x minus 3 plus x is equal to 0. And I want to add these things together. If we look at it like this, adding two things together, we would add the numbers with the x's and get an x number. And then we add the numbers that don't have x's and get that number. And we put them together. Okay. Same thing here. The numbers with the i's, that is the imaginary parts, we add those coefficients together and keep the I on it. And then the numbers that don't have the i's, we just add those numbers together like you'd normally add. And so you get the answer like this. So for example, let's say we have z1 is 4 plus 2i, and z2 is minus 3 plus I. And I want to add these two things together to get a final answer, z3. So z3 is going to be, well, I add the real parts together, so 4 plus negative 3 is equal to 1. And I add the imaginary parts together, 2i plus I is 3i. And so there's my answer. 1 plus 3i would be the complex number, which is the sum of these two complex numbers. Okay, so thankfully we're used to vectors by now. You're used to x and y components when you add two vectors together. This is identical. except instead of calling it x and y components, we call it real and imaginary parts. Now, we can go from there even further and talk about what happens if we want to multiply complex numbers together. So for instance, let's say we have I times I. What's the answer to this? This is the most basic one we can do. And well, this is fairly easy if we think about it like this. Square root of negative 1 times square root of negative 1, which is the same as the square root of negative 1 squared. We have to be careful formally, mathematically. I am kind of hand-waving slightly, but for our purposes of just learning this right now, this is perfectly fine. The square cancels the square root, and we get negative 1 as the answer. Of course it is. We know that's the whole point. I squared is negative 1 because I is the square root of negative 1. So you square it, you multiply it by itself, you get negative 1 as the answer. That was the solution to the original equation, if you remember. X squared is equal to negative 1. What number do you multiply by itself to get negative 1? We said it is I. That's the definition of I. Okay, well, what about if we have something else? Maybe some number, C, times complex number Z. Okay, so a real number C, and we're going to multiply that by the complex number Z. Well, that means Z times A plus IB, right? And thankfully, the distributive property works here. And we say this is A times C plus I times C times B. Okay? So just like you would expect, if you think about this as, you know, the I is like a variable X or something, you don't have to worry about what I means. You just think of it as a variable. If you're going to multiply a number times a binomial, you just distribute the number in, multiply it by both pieces of the binomial. All right, what about if we have Z1 times Z2? Okay, so now we have a complex number times a complex number, getting slightly more complicated each time. Well, let's look. A plus IB times C plus ID. Okay. Well, how do you work with this? Again, the distributive property works. Also, we could think of this as foiling, if you remember from high school algebra. You multiply two binomials together. So we say the first term times the first term is A times C. Then you have the first term times the second term. So that's plus I times A times D. Then you have the second term times the first term. So you get I times B times C. And then lastly, the second term times the second term, which is I times B times D. Okay? Cleaning this up a little bit, we have A times C. Plus, notice we have two terms here that have an I on it, so we could factor out the I, and this becomes AD plus BC. And then the last term has I times I, which is I squared, but we know I squared is negative 1, so we just say it's minus B times D. So the final answer is AC minus BD plus I times AD plus BC. Okay. Now, this isn't something to try to memorize. This isn't a formula or something you need to remember so that when you see two things, you remember, oh, it's going to be AC minus BD plus, you know, don't worry about that. This is just a general look at how to do this. If you do, if you just have general variables here. If you have the actual numbers, you're just plugging the numbers in. You're multiplying it just like you'd multiply in normal algebra. Thankfully, this is true. There's no fancy math. There's no new rule we have to worry about yet. It's just if you have two binomials, because you could think of a complex number Z as a binomial, A plus IB. You multiply two binomials together. You just do it just like you would normally. Foil it out or however you think about it. Okay. Now, with that said, are there any other kind of new mathematical things that come with complex numbers that may not be true of real numbers? You know, who's to say that once we've upgraded our number system to include this new class of numbers called complex numbers, that there's not some new operations we've never heard of before. We have addition and subtraction, multiplication and division, things like this. Well, there's no reason to think that those are the only operations ever going to be invented in all of mathematics. It's just that those are the operations that matter for real numbers. It might be, and indeed is true, that there are new operations because we've included this new set of numbers, and these operations work with this new set of numbers, but they don't mean anything for the old set of numbers. And so an example of this is what's called the complex conjugate. Complex conjugate. All right, so the complex conjugate. How do I represent it in terms of writing it down? Well, we have the complex number z, and if I want to do the complex conjugate or take the complex conjugate or find the complex conjugate, it's all different types of ways of saying it, we represent it by putting a little asterisk up top, a little star up there. And what does that mean? Well, if we say z itself was the number a plus ib, then the complex conjugate of z is the identical number, except everywhere you see an I, you change its sign. So, if z is a plus ib, then the complex conjugate of z is a minus ib. Okay? Notice, this is a new operation that we've never heard of before because it doesn't do anything to real numbers. If we have a real number c, and we take the complex conjugate, well, it's just c. There's no I anywhere, so there's no sign to have to change. It's only when we include the imaginary piece of a number that now we have to worry about whether the sign changes or not. So this is a new operation, something different from the other ones we've seen. It only affects complex numbers at this point. And how do you do it? It's very, very simple. If you see an I, make it negative I. If you see a negative I, make it positive I. That's it. Now, what's so great about it? Who cares? Why is this invented? Well, it turns out if we look and we take z and we multiply it by the complex conjugate of itself, what does this become? Well, we have a plus ib, and we're going to multiply it by a minus ib. Now, if you look at this, and you remember high school algebra, which is probably a long time ago now, if you have something like a plus b times a minus b, that was a very special multiplication of binomials because terms cancel out. And you get a squared minus b squared. Okay? So it's very nice. Instead of having all the cross terms, you just have two terms. Well, what happens with complex numbers? Let's see. A times a is a squared. A times minus ib is minus I times ab. Ib times a is plus I times a times b. And then ib times minus ib is minus I squared b squared. Okay? Now notice this term cancels that term. And we get a squared minus I squared b squared. But I squared is minus 1, so a squared minus minus becomes plus b squared. And so look what happens. You have two complex numbers. One is the complex conjugate of the other, specifically here. You multiply those two complex conjugates together, and you get a completely real number. Real. There's no i's anywhere to be seen in the answer. So this, when you start using this in practice in physics, sometimes it's called the magnitude squared of the complex number z. And so sometimes we write it as absolute value of z squared, like this. And if you remember vectors, when you go find magnitude and direction, the magnitude, put it in a different color, was x squared plus y squared square root. gives you, magnitude of your vector v. Well, if we square both sides, right, the little square root goes away, and you have just the x squared plus y squared. Okay? So notice it's very, very similar. You have a vector which has x and y components. You want to find the magnitude, that is the length of this vector, or the magnitude of the vector. Well, you square the x component, and you add it to the square of the y component, and that gives you the square of the vector. You can then take the square root to get the magnitude of the vector. With complex numbers, it's very similar. Again, instead of x and y components, we have real and imaginary numbers. You take the real squared plus the imaginary part squared, and that gives you the magnitude squared of the complex number z. And in practice, the way you do it is it's z times its complex conjugate. It's a very, very special thing to do. Now, you don't have to only ever multiply the z by its own complex conjugate. Of course, you could have z1 multiplied by z2's complex conjugate. Now, that's not going to necessarily be a real number. That probably will have imaginary pieces. It's just that when you multiply a number by its own complex conjugate, you guarantee to get rid of all imaginary parts. And you basically get the magnitude squared. So, with that, we have all the operations we're going to need at this point for how to work with complex numbers. You have some number z and maybe some other number z2. They have real and imaginary parts. What can you do with them? You can add them together, you can subtract them, you can multiply them, you can divide them, you can take the complex conjugate. Now, next time what we're going to talk about is investigating more into how to think about these complex numbers as vectors, right? And what we're going to find is we can imagine, well, we've always known what's called the real number line. Right? The real number line says, okay, here's 0, and then we have 1, 2, 3, and then over here we have -1, -2, -3, and there's a pi somewhere over here, there's pi there, and so forth. Well, that's fine. That's a one-dimensional number thing. Every number, every real number, lies on this one-dimensional line. Somewhere on the line, either to the right or to the left, somewhere, you'll find your number. However, now that we have complex numbers, we have a whole bunch, infinite number of numbers that you cannot find on this line. For instance, I don't know where is I. I will not be found anywhere on this number line. So what mathematicians did, which is very interesting, is they said, well, what if instead of thinking about numbers as lying on a one-dimensional line, instead we think about them in a two-dimensional plane. So now what we have is the x-axis of this coordinate system being the real number line, and the y-axis we'll call the imaginary number line. And so here we'll have I, 2i, 3i, and so forth. And then down here, -i, -2i, and so forth. So very similar to the real number line. It's just the number line on the vertical axis has i's on it. And so if what we want is some number z, being a plus ib, now we'll be able to find this number. It'll be somewhere over here, for instance, where this number here is I times b, and this number over here is your a, right? And what we're going to do next time is say, hey, look, what we can do is use all of our knowledge about vectors and think of a complex number as the vector which points in this complex plane. And once we can do that, now we can definitely think about manipulating complex numbers exactly identically to how we manipulate vectors. And we have all of that math at our disposal already. So that's what you can look forward to in the next lecture. I hope this has been helpful. This is definitely a very, very important subject. If you have any questions, let me know, and I'll see you next time.